Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Michael Niemack, who is Associate Professor of Astronomy and Physics at Cornell University. His research interests include cosmology, inflation, dark energy, dark matter, neutrinos, galaxy clusters, and galaxy evolution using cosmic microwave background, CMB, and other submillimeter measurements. Welcome, Michael.
Thank you. It's a pleasure to be with you.
Yeah, thanks for doing this. So before we get into some of the exciting things that are going on the technology side in Chile and elsewhere, I want to sort of set the stage for CMB, the cosmic microwave background. So the little I understand about this, Michael, we had something happen 13.8 billion years ago. The universe formed. We don't have a very good idea of what might have happened in the very initial parts of universe's evolution, but around 380,000 years, we had a plasma of photons and baryons, and at that time frame, approximately, atoms started to form, and the photons that were getting bumped around till then were escaping as light. And they've been traveling approximately 13.7 billion years now, and got to sort of tired, I guess, and and the wavelengths extended all the way to the microwave region. So that is what we call the microwave background radiation, right? So there is a rich history around this, starting in the 1960s.
Yeah, that's right. And even a little earlier, I would say, about 100 years ago, was really the beginning of modern cosmology, when the first evidence was discovered that the universe is expanding and that we live in a dynamic, changing universe, which was contrary to the beliefs of most scientists around that time.
Yeah.
So then the discovery of the cosmic microwave background in the 60s, this kind of accidental discovery of this, what Penzias and Wilson first thought was noise in their telescope in New Jersey, because they just saw this background temperature apparent in every direction that they looked. And so they cleaned all the bird poop off of their telescope because they thought that might be contributing to it, and shot all the pigeons that had added to that, right? And
it's a bit like static on the TV.
Yeah, exactly. It's like seeing static on the TV. And actually, in older television, some of the static that you did see when having the television tuned into a channel without any signal on it is cosmic microwave background photons that make it through the atmosphere and excite the static in your television. So, right. I mean, this leftover light, this very cold few degrees, around 3 degrees above absolute zero or minus 270 degrees Celsius light fills our universe and was discovered back in the 60s. And then a variety of discoveries have been made in this light over the last 50, 60 years since then. First, it looks like this incredibly uniform temperature in every direction we look. But about, a while after the first discovery, I think it was in the 70s, the first detection of non-uniformity or non-isotropy was discovered, where we actually have an apparent red shifting of the light in the direction that we're moving away from, and blue shifting of the light in the direction that we're moving towards on Earth. And that's dominated, our understanding is that's dominated by the motion of, our galaxy in particular, relative to the rest frame of the cosmic microwave background, or this reference frame that the cosmic microwave background was emitted in. So I still just find that to be a remarkable discovery and a remarkable fact that there actually is a preferred rest frame in our universe. And that is the rest frame defined by the cosmic microwave background. And if you try to move too fast relative to that rest frame, well, this light that has been stretched out into these very long microwave wavelengths, much too long for us to see, will get blue shifted more and more. It would get blue shifted into the optical so that we could see it. And then if you went even faster, now this is, very, very close to the speed of light we're talking about, but faster and faster, then you would blue shift it into X-ray and gamma ray light photons that would most likely destroy whatever spaceship or anything that you were traveling in. So there's some, very practical aspects of this being a preferred rest frame in our universe.
So we'll talk about the measurements soon. I just have a couple of conceptual questions. So
sure.
So do we have to, I know that Planck satellite and others measure this. So when we measure this, do we have to correct for some sort of galaxy motion in it?
Yeah. When making measurements with a satellite, we do. Okay. Because this motion is something that we only observe on the very largest scales, right? There's one direction where it's blue shifted a little bit, and one direction where it's red shifted a little bit. Those two directions are opposite of each other because of our motion through this celestial sphere, right? And that signal needs to be removed to extract the very largest angular scale signals in the cosmic microwave background. Now, when we're making measurements from the ground, the atmospheric signals are large enough that we don't have, we're not able to reconstruct those very large angular scale signals, this so-called dipole from the motion of our galaxy. So it's we don't really have to worry about it for ground-based measurements because it would be so hard for us to measure anyway.
We had the accidental discovery in the 60s. And then there were a couple of satellite-based measurements on this, right? One is, was it COBE, the first one?
Yeah, right. So COBE in the 90s, and then WMAP, the Wilkinson Microwave Anisotropy Probe that released its results in the early 2000s, and then the Planck satellite as well, that released its results around 10 years after that.
Okay, and so the most of the pictures that we see in scientific literature and so on, that is made by Planck measurements, right? Is that the one that we typically see?
Yeah, these days, over the last since over the last 8 years or so, anyway, the Planck satellite measurements of the cosmic microwave background have become the most popular.
Okay. And now you and others are involved in making this a lot better. So you had a paper in 2015, 2016 entitled Designs for the Large Aperture Telescope to Map the CMB 10x Faster.
Mm-hmm.
You want to talk a bit about that paper and what the motivation was?
Sure, yeah. So, right, I mean, these satellite projects have made enormous progress and critical progress in our field, with building on each other, each one being substantially better than its predecessor. And in particular, COBE made the first measurements of these variations in temperature from the cosmic microwave background, these anisotropies, because they're deviations from an isotropic or uniform temperature, that had ever been observed beyond the dipole that we were discussing earlier. So primordial anisotropies due to variations in the density and velocity fields in that plasma that you described in the early universe. And so those leave this tiny imprint on the cosmic microwave background. And so WMAP and Planck both made substantial improvements in the measurements of those anisotropies, and led to this remarkable cosmological model and kind of bizarre cosmological model that we're still trying to understand, where our best description currently is that the universe is dominated by this dark energy that makes up about 70% of the energy in the universe. And then most of the rest is dark matter, cold dark matter, with only about 5% of the energy density in the universe made up of all of the regular matter, or that we call baryons. Yeah. Everything that we see and know and love in the universe, right? All the stars and everything that emits and interacts with light. So anyway, that's lots of progress was being made, in part because of, two main things. One was increasing the size of the telescope apertures that was being deployed on these satellite observatories, and the other was improving the sensitivity of the detectors that were being installed on those telescopes, like cameras that we have, everywhere in our phones and on regular optical telescopes on the ground today. So those two advances are really what this paper was about, pushing forward from ground-based observations. And one of the reasons why it's so important to move to the ground, one, it's many times cheaper, somewhere between 10 and 100 times cheaper than flying satellites. And two, we can build much larger telescopes from the ground. That's why in the title there's this large aperture telescope. So a scale of telescope that is particularly useful for these measurements, we're not talking about huge telescopes, but is 5 to 6 meters. And so 5 to 6 meter primary mirror apertures. So, go ahead.
Yeah. So quick question. So the sort of the environmental disturbances we worry about for optical telescopes and all of that, it's less of a concern in this case?
It's just different kinds of concerns that affect the performance of our measurements. So with optical telescopes, what's often limiting the performance of the measurements is often referred to as the seeing, which is like the twinkling of stars due to atmospheric fluctuations. And that twinkling actually diffracts the light because of variations in the atmosphere up above you, and makes it so that the optical telescopes cannot usually achieve as good optical performance as they're designed for. So in the microwave measurements, it's a little bit different. We don't see twinkling, but we do see actually emission from the atmosphere. And in particular, we see emission from oxygen and water atoms in the atmosphere. And so that's really what drives us to build these telescopes at very remote, high elevation, and extremely dry sites on Earth. So we actually build and deploy optical telescopes at different sites where there's that typically aren't as high elevation, but there's extremely uniform atmospheric conditions, versus for microwave sites, we're building them as high as we can go. So these telescopes in Chile, the Atacama Cosmology telescope that I've been working on for almost 2 decades is at about 17,000 feet elevation. And 2 of the new observatories we're working on, one will be right next door, the Simons Observatory. And then there's the CCAT-Prime project that I'm also playing a big role in, and is led by Cornell University, that will be built at around 18,000 feet, 400 feet elevation, 5,600 meters, also in Chile, and one of the driest high elevation deserts on Earth.
Okay. So I want to get to those things. So the basic idea here is that build the telescopes on Earth, get them to a place that's high and dry so that you can remove some of the disturbances, and make them bigger so that you can actually get a higher definition. And the goal here is to have a higher definition of the CMB than we currently have.
Yeah, it's both to have modestly better angular resolution, so angular definition, as well as to have much more precise measurements. And so that's where the mapping speed part of that paper title came from, to have 10 times, to be able to map the CMB 10 times faster. What we actually need to do now is build and deploy many more of these microwave detectors than we've ever been able to before. And so this paper was about telescope designs that are at the 6-meter scale, and we'd built 6-meter scale telescopes before, but we'd never built 6-meter scale microwave telescopes that could illuminate on order 100,000 microwave detectors at the same time. The previous telescopes, the ones that are deployed now, like the Atacama Cosmology telescope, can only illuminate around 10,000 of these detectors. And we need to illuminate many more of these detectors, because we've been able to advance the detector technologies so much that we're now limited by the fundamental noise of the emission from the Earth's atmosphere. And so the way to improve upon that noise is just to have more and more measurements simultaneously, and integrate out all of the atmospheric signals, and just make more and more sensitive measurements of the cosmic microwave background, both these temperature signals and polarization signals over time.
So the current CMB, the variations in it is very minute, right? So the goal is to get to even better picture. And so the site that you mentioned, Atacama in Chile, there's a functioning telescope there, right? Atacama Cosmology Telescope, ACT. Exactly. And so how long has that been functioning?
So let's see, I started working on the design for that and I should emphasize, all of these projects are very collaborative projects with many people involved, and building on, of course, the history in this field that we've been talking about. But I started working on the design for that telescope as a graduate student when I was a graduate student at Princeton University with a research group there and my advisors there. And that was, let's see, back in 2002, and then it was first deployed in 2007 and really began observations actively in 2008. So it's been running for about 12 years now, and we've actually built 3 different generations of cameras for it, cameras and detector arrays, to improve the sensitivity of what we can measure with that telescope over time. But now we really need a telescope that can illuminate many more detectors, which is why we're building these new designs for Simon's Observatory and CCAT-Prime that should be completed in 2022.
No, these are 2 different things, right? The CCAT-Prime and Simons. Simons is currently in construction, or is it done?
They're both in construction right now.
Oh, both in construction. Yeah. Okay. And both are on the same site, slightly separated, right? So is it like a few miles, or is it much bigger than that?
Let's see. It's probably, only about 10 miles of separation, although it's also about 1,500 feet or 1,600 feet of separation in elevation. Okay. And remarkably, even that going from 17,000 feet elevation to 18.6 thousand feet elevation actually makes a significant difference in the amount of water that we have to look through in particular. And so that improves our ability to make measurements at slightly shorter wavelengths than we have been with the Atacama Cosmology telescope. We refer to them as submillimeter wavelengths. So most of the measurements, to clarify that we're making are wavelengths of light right around a millimeter long. So, a millimeter to a centimeter. So very
very low
imaginable scale, right? Yeah, physical scale for us as humans. Whereas the light that we observe with our eyes is thousands to 10,000 times shorter wavelength than that. So much smaller wavelength than, you could see an object of that scale with your eye for optical wavelengths. So we're with the CCAT-Prime Observatory, we're specifically pushing into from millimeter wavelengths to slightly shorter submillimeter wavelengths, which opens up a variety of new astrophysical windows that we can explore and study beyond the CMB measurements.
And so CCAT is at a slightly higher elevation than Simons?
Yeah.
And so for my own understanding, Michael, so you're getting data from a lot of different sources, Planck data is there originally. So is this data being combined to make it more useful? Does the new data allow to remove some of the errors from the previous data? How would the ultimate, the better picture, so to speak, evolve?
Yeah, great question. And there's actually just over this last summer, there's been a lot of really exciting progress in both comparing our measurements with the Atacama Cosmology telescope to Planck data, and in combining them and using the combination in some new ways. So I'd like to start with talking a little bit about the comparison, because it's actually pretty cool, I think, and ties back into this original discovery of the expansion of the universe 100 years ago by Edwin Hubble. And we are still trying to improve our measurements of the Hubble, what's called the Hubble constant, the rate at which the universe is expanding today. And there's been this controversy brewing in our field over the last few years, where the measurements of the Hubble constant from the Planck satellite were coming in a few kilometers per second per megaparsec is this kind of funny unit that we use to quantify it, but that's measuring how fast things are moving apart from each other at these great distances between galaxies. So it's coming in slightly slower expansion rate than was being measured by all local measurements, including measurements of supernova that, they're not that close, of course, but compared to the cosmic microwave background, they seem very close and local, as well as these new gravitational lensing techniques that different groups have been using. Anyway, there's this tension between the two measurements that doesn't fit well with our dark energy and dark matter dominated cosmological model. And so the two different groups on different sides would say, oh, there's probably a problem with your data, or there's probably, and just pointing fingers a little bit. I mean,
it's like
for the most part,
67 or 74 or something like that.
Yeah, exactly.
Yeah, okay. So we say it's good enough for government work, but that may not be for physics.
Right. I mean, well, the alternative is that there's something fundamentally new in cosmology, that this dark energy is acting differently than the simplest possible description, which is what we've been able to fit all our data with so far, that it's just a so-called cosmological constant, or that there's some new particles that we don't yet understand and that don't fit within the standard model of particle physics. Or there's a variety of other explanations, and nothing has been found that just resolves this tension perfectly yet. But it's really, if that's the case, then it's tremendously exciting for our field, right?
Are the error bars overlapping, or are they kind of distinct?
No, they're not overlapping between some of the most advanced supernova measurements and the Planck measurements. They're in tension at somewhere. How we described it is with. Well, I'll just say is they're in, 3 to 4, maybe even a little bit more sigma tension with each other. So if there's not some weird systematic in one of the data sets, the chances of this being just a statistical difference are getting vanishingly small.
So if you assume both of those measurements are right, then you have to come to some sort of conclusion as to whether something is changing, because one measurement is close enough and other is too far. So something has changed or something is changing, something along those lines. So that's what you call potentially new physics.
Yeah, then exactly. If both the measurements are right, it seems like there's new physics to be found. And to be discovered, and that is different from any models that we have been using so far. And I should add, recently, just last year, there is another group that used a different calibration method for their supernova analysis, and their value comes in between the Planck and the Rees et al. Group. This is a Friedman et al. Paper. So, there's some people who think that now that there's likely a systematic problem with the supernova data, although that's not the only local data set that's coming out with this higher value. Anyway, so with the Atacama Cosmology Telescope, it's really hard to get an independent check on the cosmic microwave background measurements. And that's one of the things that we are uniquely positioned to do with the Atacama Cosmology Telescope, because no other observatory is measuring such large areas of the sky with the kind of precision that we are with the ACT. And so just over the summer, we had our first results come out on improved constraints on the Hubble constant, independent of Planck. And
Yeah.
while our uncertainties aren't quite as small as Planck yet, we have enough data that they should get basically as small as Planck, possibly even a bit better than the Planck satellite. But remarkably, our value came in extremely consistent with the Planck measurements. And there were people previously on the optical side or the supernova side saying, oh, it's probably a problem with how Planck analyzed their data. So now, you know, and we didn't know. We did a completely blind analysis. There's some people within our collaboration who thought that was the most likely outcome too, even. But we came out with results that are completely consistent with Planck so far. We'll see if that continues to hold once we analyze the several additional years of data that we've collected but not analyzed yet. But it's an exciting time for these comparisons and for this field with this oldest parameter in cosmology, the Hubble constant.
So if you get the averages and the variance roughly the same between Planck data and yours from ACT, then the chance of systematics in either case is substantially lower, right? If you're getting the same results.
Exactly. Yeah, and
it's two different perspectives too. One is from the satellite, and one is from the ground.
Exactly. Yeah, and we're actually the data that it's coming from, or the measurements that the strength of this constraint on the Hubble constant is coming from, are actually somewhat different, where we are becoming more and more sensitive with ACT to the polarization and isotropies in the cosmic microwave background, whereas most of Planck's signal and constraints come from the temperature measurements. So while those are related to each other, the physics behind them is related, there's multiple checks occurring here that enable us to build confidence in these results from the cosmic microwave background.
So that's one of the goals, to sort of get a higher precision on the constraints on Hubble constant.
Mm-hmm.
One of the other things, if I remember correctly, so there was a hypothesis around the polarization, right? It might actually prove the inflation hypothesis better. So is that part of Simon's, or both CCAT and Simon's?
That's more part of Simon's. There's potential that we'll be able to help with CCAT as well. But this is an interesting difference in how we go about those measurements. So those measurements are focusing on one particular angular scale in the sky that is around 1 degree angular scales. And that is, so the moon is about half a degree, and the sun. That's why we get eclipses, of course, since they're about the same size. But so it's about, we're looking for signals on the sky that are about twice the diameter of the moon on the sky. And we actually don't need telescopes as large as 5 or 6 meters for to resolve that kind of angular scale. And it's actually advantageous to have smaller telescopes for that, because we don't have to calibrate them over as large of a range of scales. So for Simon's Observatory, we're building a few half-meter aperture telescopes. So about 10 times smaller aperture telescopes, going specifically after this polarization signal that might have been generated due to gravitational waves that were produced during this epoch of inflation in this first tiny fraction of a second after the Big Bang.
And so the intuition there, Michael, is that when there's gravitational waves, it sort of makes the light turn or curl or whatever.
Yeah.
Is that the idea?
Yeah, exactly. And so, right, these gravitational waves, I mean, there's been a lot of excitement about gravitational waves in the last few years, of course, because they were first detected directly by this LIGO interferometer. And providing, measurements of black holes colliding and then neutron stars colliding for the first time. And so those gravitational waves are actually, as they propagate through the universe, either from black holes or neutron stars or from inflation, are actually causing expansion and contraction of space as they travel through the universe. And as a result, the possible gravitational waves from inflation, if they exist, and we don't know that they do necessarily, but it's one of the predictions of inflationary models, then as they're causing this expansion and contraction of space, they will actually convert some of the linear polarization in the cosmic microwave background into a different pattern that has this kind of curl pattern that you were referring to, that we often refer to as a B-mode pattern, just because of historical conventions, because it's mathematically analogous to magnetic fields, which we use B. Anyway.
So the idea is, if we find B-mode polarization there, then it actually provides a higher level of confidence in the inflationary hypothesis. I know that there was some attempts from the South Pole to measure this, and potentially a false start there.
Right.
So do you want to talk a little very quickly about what happened there?
Oh, sure. Yeah. So there have been attempts both from Chile and from the South Pole, but in recent years, the groups at the South Pole have been making the fastest progress on this, and I think with Simon's observatory, we expect to catch up and even exceed the progress that they're making from the South Pole. I'll just really briefly mention, the South Pole is another really great site for these measurements because it's also relatively high elevation and extremely dry in the winter. This group, the BICEP collaboration, has been observing with similar kind of half-meter scale telescopes from the South Pole for many years now. And just before one of the big Planck satellite releases, they announced that they thought that they had detected these so-called B-mode polarization signals, this curl pattern in the polarization on degree angular scales, on this angular scale that I was referring to, that we expect to see signals if the gravitational waves from inflation were strong enough. There was tremendous excitement about this, press releases going out, talk of Nobel Prizes and things. It turned out that when proper analysis was done with the Planck data, that all of their measurements were completely consistent with cosmic dust within our galaxy, which can also generate the curl patterns like this just through random chance. So that was a bit of controversy, and many people in the field, there were very strong views about how all of those results were initially presented.
But disappointments like that actually provides, sometimes a better way to look at things. So yeah. Simon's could potentially have the same issue, right? Simon's information?
Yes, it could. Although one of the biggest problems with the BICEP results was that they did not use enough measurements at different frequencies or different wavelengths of light, spanning all the way from 1 millimeter to 1 centimeter wavelength. They were only focusing on 2 millimeter long wavelengths in particular. And why this is important, why you want multiple wavelengths, is because the cosmic microwave background, because it's so cold, will look very different at different wavelengths. It will become brighter around 1 to 2 millimeters and much dimmer at the longer wavelengths. And versus dust from our galaxy, well, it will get progressively brighter and brighter for the most part as you go to the shorter wavelengths. And so by measuring the signals at several different wavelengths, you can really disentangle the contributions from galactic dust from the cosmic microwave background. And so that's part of the plan for Simon's Observatory from the start. And they've been doing this since that first announcement at the South Pole also. But with Simon's Observatory, we'll actually be observing with 6 wavelengths simultaneously. And so we should be able to characterize galactic dust, as well as radio emission is another concern that gets brighter at the longer wavelengths, and remove those kinds of signals from the cosmic microwave background.
Is it one telescope or an array of telescopes?
So for Simon's Observatory, we'll have one of these 6-meter aperture telescopes that evolved from the design that I studied a few years ago that we were discussing earlier. And then we'll have an array of starting with at least 3, or if all goes well, 4 of these small aperture half-meter scale telescopes that will just sit side by side and be operated independently, but observing the same regions on the sky.
And combined in some fashion.
Yeah.
So are there other objectives other than the CMB for the Simons?
Well, there's one of the really great things about the CMB is there's a tremendous amount of information that we can extract from these millimeter wave and submillimeter wavelength measurements. Yeah. So we're, of course, trying to measure these primordial signals from the CMB and go after understanding our universe as a whole in the inflationary epoch, the expansion today, and the Hubble constant, dark energy and dark matter. But we're simultaneously measuring a wide range of other astrophysical phenomena because of both emission from those objects, as well as how those objects affect the cosmic microwave background as the cosmic microwave background light passes through the objects. So one that my research group is particularly focused on is galaxy clusters. So these are the largest gravitationally bound objects in our universe, where they have somewhere, hundreds to even on order 1,000 or more galaxies that are gravitationally bound to each other and orbiting around each other and occasionally colliding, like in some of the beautiful optical images that we see sometimes. And so these clusters of galaxies will actually leave shadows in the cosmic microwave background. And what they'll do really is hot electrons in the space between the galaxies will give a little boost in energy to some of the cosmic microwave background photons. And so that makes it look like a cold spot to us at 2 millimeter wavelengths and a hot spot at 1 millimeter wavelength. So by measuring by measuring large areas of the sky, and this is something we can only do with the larger aperture, the 6-meter scale telescopes, we can see these cold spots at one wavelength and hot spots at another. And we've discovered many new galaxy clusters through measurements like these with the Atacama Cosmology telescope. And with Simon's Observatory, we'll discover thousands more. So we now have the largest catalog yet, with around 4,000 galaxy clusters in it, of galaxy clusters detected in this way from the Atacama Cosmology telescope. And we'll get up into the tens of thousands with Simon's Observatory and the CCAT-Prime project, and future measurements.
Does it give any insights into sort of the dark matter distribution or anything like that?
Yes. So there's things we can study about the distribution within these galaxy clusters. We can actually observe gravitational lensing due to the dark matter distribution within them, and gravitational lensing of the cosmic microwave background itself, which we've contributed to some interesting papers on. And then we can measure, well, the gravitational lensing of the cosmic microwave background as a whole, and use that to improve our understanding of this cosmological model, this dark energy, dark matter dominated cosmological model, because there's robust predictions about what we should see when looking at the gravitational lensing of the cosmic microwave background. And this is really a unique way to measure our universe compared to any other probe of the dark matter, because we're measuring the most distant light in the universe. So it is, in effect, being lensed or shifted, by all of the observable mass within our universe. Right. And there's no other source that's true of. So this is very complementary to other measurements that are being done at other wavelengths, but it's anyway, it's a cool and a unique effect for us.
So I know that at the conceptual level, the lambda CMB is pretty well. It's accepted, but we don't have a good idea of what makes up the dark matter, right? So there are a lot of hypotheses around that. So would this give any indication of? I know that neutrinos, WIMPs, primordial black holes, a lot of these people think about. Will this give any additional insights into that?
So there's a couple of different ways that CMB measurements have the potential to provide more insights into that. One is that the certain types of particle dark matter in the early universe can affect the spectrum of these anisotropies that I was mentioning earlier in the cosmic microwave background. And so if we can potentially provide evidence that new particle species exist through that, then there's also means of constraining dark matter through some other interactions that occur and leave an imprint on the cosmic microwave background. But there aren't with current projects, there aren't like direct, we will measure this particle through the CMB and know exactly what particle it is to really differentiate between the wide range of possible dark matter candidates. We may be able to help narrow the range down with CMB measurements, but we really need the direct detection dark matter measurements that other research groups are pursuing to search for the WIMPs or the axions or whatever it may be as well.
So with COVID-19, do you still travel to Chile or things?
No, we've all our travel to Chile has been shut down. But fortunately, we have a really excellent team based in Chile, working on the Atacama Cosmology Telescope and on Simon's Observatory and CCAT-Prime towards building those two projects. So we've been able to, well, things have been slowed down a little bit. We've been able to continue making really regular observations with the ACT. And so we're acquiring lots of new great data. I was actually last down there in January, aiding with the deployment of our longest wavelength detectors on the Atacama Cosmology Telescope yet, these centimeter scale detectors. And so we're really excited to get those installed and start making measurements at these two new wavelengths. And I'm very pleased that we're able to continue the observations and get, a solid year of observations with that camera, despite the challenges we're all facing.
Yeah, so you're involved in all these exciting things. So based on your experience on this, if you look forward 5-10 years, where do you think we're going to end up? There are some questions around the Hubble constant, different measurements showing slightly different values. There is a dark matter, I should say, kind of hanging about. So where do you think we might be from an experimental perspective, let's say 5 years?
Oh, it's a great question. I mean, and I think, cosmology is, well, we are in, I think it's fair to say, a golden age of cosmological research. It's still a relatively slow-moving field because we're dealing with, really large-scale measurements and measurements that are challenging to tackle. But I'm optimistic that we may see one or more major breakthroughs on the 5 to 10 year timescale. It may be a little bit longer than that, but there's so much unknown still. I mean, we have this beautifully fitting lambda CDM, dark energy, dark matter, dominated cosmological model that fits so many data sets, from the cosmic microwave background to consistence with particle physics to optical measurements of galaxies and the evolution of our universe. But there are these holes in it, and there's these huge unknowns. What is dark energy? What is dark matter? How did the beginning of the universe really get started? Is inflation the right paradigm for what happened at those early times? There's, we could make a breakthrough in any of those areas, over the next year or 5 years or 10. I'm very excited about the potential for progress in cosmic microwave background work, of course, but these direct dark matter experiments, as well as contributions from astronomical measurements at other wavelengths, will be key for advancing all of these things. And any one of them could provide the next major breakthrough. We'll see.
What's your intuition, Michael? Will we move toward new physics, or better and finer data will essentially confirm the status quo? What is your intuition?
Oh, I mean, I think I think both will occur at some level. I think the model is solid, and it's not going to, I would be very surprised if there's dramatic changes to it. On the other hand, there may be major surprises. For example, we say this dark energy and cosmological constant dominate the energy budget of our universe, but that allows for a huge range of possibilities in what the dark energy could be. And it may not make sense to call it dark energy anymore when we refine our models and improve our data sets. But that really remains to be seen. I mean, there's also, it's really remarkable that there's these two epochs of exponential expansion in the very early universe and occurring now today. Is there a connection between them? We don't have a reason to believe, obviously, that there is, but there could be. We just don't have data that really supports that. So I think it'll be an exciting time for learning about new physics of our cosmological model, and both that and refining our understanding of the current model in the coming years.
Yeah. Excellent. Yeah. Yeah, it's exciting. Thanks again, Michael, spending time with me, and good luck with all this research.
Thank you, Gill. It was great talking with you.
Thank you.